All right, we're a minute after, and I'm sure there may be one or two that folks that come in, but in the interest of using our time wisely, let's get this thing started. First of all, thank you all for joining us today for our webinar, Industry 4.0, Product Validation and Process Virtualization. This is a joint effort by Sandalwood and Flex Structures, a couple of companies that have partnered here in North America to provide solutions in an interesting part of the Industry 4.0 space. Our agenda today in the 90 minutes that we have will be to introduce ourselves. We're going to talk about our segment of Industry 4.0, which includes a number of topics that are also bundled under new manufacturing technology, IoT, integration design, cybersecurity, AI, machine learning. Our focus today will be on product validation, process virtualization, as that is used to improve both product design and assembly and manufacturing of products. We'll touch on a number of use cases related to product design and virtualization, and leave some time throughout for questions as well as comment and interaction with presenters. There are a couple of housekeeping notes. You should have a chat window available to if you need to send a message over to myself or John Lukowitz or Kyle Palferman, our other panelists here today. We've also got a Q&A chat that I'll be monitoring as well once I stop talking here today. So with that, our collaboration and myself, I'm Carl Bangert, General Manager of Flex Structures North America. I'll say a few words about us. Our webinar today is hosted by our friends and partners, technical partners here in North America, Sandalwood Engineering and Ergonomics. John and Kyle hail from there. I'll turn it over to John to say a few words about Sandalwood Engineering. John.
Thank you. Thanks, Carl. Good morning, everyone. If you're unfamiliar with Sandalwood Engineering and Ergonomics, we are an engineering services firm. We were really born out of Ford's Advanced Manufacturing Technology Division. We were founded in 1989, so we've been around for quite a while, working with a variety of clients in a variety of industries. We have offices throughout North America, so locations in the US, in Detroit, Michigan, as well as Louisville, Kentucky, and in Canada, in Toronto, as well as in Mexico City. Sandalwood is broken up into 3 lines of business. So those are injury prevention, which is primarily focused on things like safety and ergonomics, systems engineering, which is focused on things like manufacturing, project management, as well as these advanced simulation tools, some of which we'll be seeing today, and systems integration, which is primarily focused on controls engineering. So what do? Sandalwood utilizes these advanced technologies to assess and manage risk for our clients, employees, processes, and systems. And we're very happy to be here with you today.
Thank you very much, John. I appreciate that. We'll be hearing more from you in a very little while. Myself, I'm with Flex Structures, which is founded actually in Germany. We celebrated our 10th anniversary this year, based in Kaiserslautern, a high-tech spin-off of the Fraunhofer Gesellschaft, which is a renowned German institution that works on government and academic and industry collaborations to develop new technology, and then to work with spin-offs such as Flex Structure to bring this technology to market. Some of the early work that is part of Flex Structures is the real-time simulation of cables and other flexible items, that hoses and so forth, which were seen as integral to the advancing electrification of vehicles and products. I'll touch on that later. In the 10 years that we've been around, we've expanded with offices throughout the world, partners in the Far East, and here in North America in the last 2.5 years. As I said, we've partnered with Sandalwood Engineering and Ergonomics because their skill set really aligns well with the products that we've developed at Flex Structures. And really the motivation for this, as you've seen if you're from the Southeast Michigan area, but really you're seeing this in products all around, is the advanced electrification and complexity of transportation systems. We've gone from a few feet of cable in cars to miles, actually miles of cable and wiring, along with an increase in the number of sensors, software needed to control these advanced vehicles. And as we move toward self-driving and so forth, it will only increase. The OEMs, as well as new upstarts in the electrical vehicle market, are seeing this as the future. Everyone's in. Our Detroit 3, as well as companies throughout the world. And this presents a challenge because managing this increased complexity is difficult if you wish to get vehicles out in a timely manner. So what we're going to discuss today is we're going to reference really some of the success that our clients have had in taking the traditional physical prototyping approach, where you've got to create a mock-up of assembly, let's say a front suspension of a car and the brake hoses and sensor cables and so forth, try to figure out where everything goes, and really get it to where these historical test labs are nearly empty, because you can do what you need to do in the virtual space, a combination of virtual product development together with process virtualization. We have an example here of our good clients at BMW, who did, in yellow, laid out some cables and hoses on a front suspension in 2015. And when they checked on what was rolling off the line, 3 years later, they were within millimeters of what they'd initially designed. This is a major accomplishment because there are so many variables, so many things that can change as you go along, that can lead to big problems as you get ready to assemble a product. And having these challenges, in grasp really this early in the product development cycle is a time and money savings. So what we're going to discuss today really touches on what's taking place in the product development space as well as the manufacturing space. So I just touched on cable simulation for managing this the vehicle electrification complexity. That leads to questions about manufacturability and assembly. How can these complex pieces and wires and so forth fit together? For that, there are solutions in assembly path planning, being able to fit the puzzle pieces together and make sure that this product can be realized. And once we've done that in the virtual world, the question still is, can somebody on an assembly line do this? For that, we have an intelligently moving mannequin in which we can do ergonomic studies, tie together the pieces we've already simulated with flexible cables, how they're assembled, apply that to our human body model, and use that really to get assurance that you can actually create and assemble this model as well. And to really bring that into where we're going with Industry 4.0, there is interest, growing interest in being able to bring the human back into this design process as well, which we support through virtual reality. So this computer model, this leverages on top of our IPS, Industrial Path Solutions platform, to be able to take a model that in the past had been strictly static and be able to manipulate that in 3D using VR controls such as commonly available with Oculus. And we'll show that. Kyle will be showing that together with John in a few moments as well. So our story begins with cable simulation, and here I'll turn off and turn this over to John. I don't see any questions right now, so John, please tell us a bit more about cable simulation.
Absolutely. Thanks, Carl. So as Carl mentioned, we'll take you through the whole suite of tools, beginning with cable simulation, moving into the path planner, talking through IMA, the intelligently moving mannequin, which is our dynamic modeling solution, and then showing how all of this can be tied together in the virtual reality environment. And we will begin with cable simulation. And in the interest of bandwidth, I am going to turn off my video and share my screen. All right. So beginning with cable simulation, we're going to go through a basic example here where we're going to try to analyze and optimize this brake line on this front corner suspension assembly here. As we go through this process, I do want you to keep in mind that this methodology and the way that the tools work really applies to any kind of flexible component. So whether that's a single wire, a multi-branch wire harness, a cable, a tube, even things like preformed cables. So if you have something that's pre-bent into some configuration, the methodology is really the same and applies to all flexible components. So to begin here, we've just imported in some CAD data, either from our CAD system, or we have seen direct connections between PLM systems and IPS. So we've seen direct connections between Team Center as well as Creo View through Windchill if you're using the PTC solution. You can also just bring CAD in directly from your CAD system. So we're compatible with a number of different 3D CAD formats, including JT, CATIA formats, STL, and VRML. I would like to mention here as well that we do have the capability to import point cloud data into the system very easily. So if that is something that's of interest, it's very easily done in the IPS tool. All right, so we have imported in some data here. And we can directly design our flexibles in the IPS tool from scratch. Or if we already have some pre-existing CAD geometry, such as this brake line coming out of our CAD system, we can simply take this information, make this just dumb CAD flexible, do our analysis and optimization, and then at the end, we'll see how we can actually feed that data back into our CAD or PLM system. So for our brake line here, I would like to make this, this cable flexible. So I'm just going to use a tool here called the Cable Finder to automatically find the geometry of this cable and make it flexible. So you can see the software very quickly has identified the center line as well as these cross sections going along the length of the brake line here. Very important to note, again, that we can simulate straight cables. So basically just, anything that would be straight when unloaded, but we can also simulate preformed cables. So if you have something like a coolant tube or a rigid brake line or something that is pre-bent into some configuration prior to installation, we can also handle those kinds of flexibles as well. Now, very importantly, we need to specify some of the material properties for this particular cable. So there's a few ways of doing this. We can directly input those values ourselves, or in this case, I'll just use the library of cables and hoses that comes with the IPS tool and identify this brake line as an 8mm brake hose. And I will hit OK. And we can see here that we have successfully created our flexible in IPS. Keep in mind that the software is very interactive and very fast. So as I move the end of the cable around, or if I were to apply some torsion to the end of this flexible, interestingly, we see that the cable is behaving based on its very specific material properties. So for this brake line in particular, it's very torsionally stiff. So if we apply torsion, the cable immediately goes into bending. So the software is highly, highly interactive and fast. Now we do have a motion in here for our spindle assembly, our wheel assembly, and we can either directly create these motions in the IPS tool, or if we have some pre-existing motion coming out of our CAD system, we can absolutely import those things into IPS and link them together very easily. That would include things, even if it's a very complex, multi-link kinematic mechanism, the software can handle those as well. So I'm just going to attach my cable to our spindle assembly here, and then just unwind it to make sure we're starting with a torsion-free solution. And if I play my motion again, we can see this cable moving along with our assembly. So beyond just being able to, sort of observe these things in the tool, we have a number of very powerful analysis and optimization tools built into the IPS suite. So for instance, we could create a visualization on this cable, essentially a color map, right? And we can look at things like stripes to take a look at torsion in the cable. We can look at any number of different forces, moment stresses. But in this case, let's take a look at the bending radius. And then we can customize this color map for whatever our particular design requirements are. So in this case, let's say that bending radius of 100 millimeters is really good. And our absolute minimum is a bending radius of 25 millimeters. If I play through the motion again, we can see this cable and this color map reacting in real time. We can also directly take measurements of values on the cable. So I can create a value measure on this cable. Again, looking at things like, elongation, contact forces, any number of different forces, moment stresses. And again, we'll just take a look at the bending radius here. 1 second. So again, if I play through this motion, these values are tracked in real time, and we can directly observe those values in the bottom right-hand corner of the screen here. Now you'll notice it's pretty obvious that we're overstretching this cable, that it's far too short, and that this bending radius is going very low as the vehicle is in operation. So in the IPS tool, we can very quickly and easily make changes to our flexible designs. For instance, I can very easily change the length of this flexible, right? Just with these up or down arrows, or I could type in some specific value, and we can see that this is improving our minimum bend radius condition here. We also have a number of powerful analysis tools to actually look at how those values are behaving over the course of this motion. So I could create a plot here of my bending radius over time to see how those values are changing as the vehicle is in operation. So we can see that I now have a graph showing my bending radius, and I can drag through and see how those values are changing over time. We can also do things like search for global or local maxima and minima, or specific values. So in this case, we want to make sure we're staying above some minimum bending radius threshold. So I'm going to search for the global minimum bending radius. And if I click find, we can see that the software has identified this exact point for us on the graph. We can see when this is occurring, and that our absolute minimum bending radius value is about 5.4 millimeters. So that is very well below our design requirement of a minimum of 25 millimeters. And I can jump the simulation directly to that point. And now if I optimize in this very worst case scenario, we should be able to be confident that our cable is going to stay above that value throughout the entire motion. So to do so, I'm just going to right click and change the length of the cable. And again, we can see that value changing in the bottom right-hand corner of the screen. So let's get above, sure. At about a length of around 220 millimeters, our minimum bending radius in this very worst case scenario is above our minimum of 25. So if we like these changes that we've made, I can just click this green check mark, and those changes will be saved in the simulation. Now playing back through my motion, we can see that this longer length has improved our bending radius, but this could also create some other concerns, right? So this increase in length may have reduced some of our clearances to some other surrounding components. So we can also take a look at things like distance measures between cables or rigid bodies in the software. So for instance, if I were concerned about my clearance from our break line here to, let's say, this piece of geometry, I can create a distance measure and just tell the software what I want it to measure from and what I want it to measure to. So in this case, this component here. And again, all of these values that we're tracking will show up in the bottom right-hand corner of the screen here, and they are all tracked in real time, very interactively as we make changes to our routings and our designs. Similar to what we did for the bending radius, we can create an analysis, a plot of both of these values now. So our distance as well as our bending radius, to make sure that whatever our design criteria are, they're being met. So now we'll have two plots here. And firstly, I want to make sure that my bending radius is staying above that minimum value. So I'll just search for the global minimum. Find that point. We can see our very worst case bending radius is above our minimum. So that's good. And now let me take a look at the distance measure. And this is going to be our very worst case clearance condition. So if I jump to that point, we can see that's a value of about 27 millimeters. And in this case, that should be plenty of clearance. So we can conclude that we have successfully optimized our break line here. Now the question is, what do we do with this information? So we've done some work, some design work in IPS. And obviously, we want to feed this information back to other designers, back into our CAD or PLM system, so that everyone can utilize this design. So we have several ways of doing this in IPS. Firstly, we are able to just export the center line of this cable. So again, we can send that out of the software in IGES, CGR, JT, STL, or VRML formats. We could also capture the 3D geometry of this cable in some particular static position. And we also have the capability to create motion volumes, right? So actually capturing all of the design space that this cable is going to move through as the vehicle is in operation. So if we create a motion volume here, I just need to tell the software what I want it to track over the motion. So I just want to take a look at my one cable here. And then I'm going to change my settings a bit in the interest of time. And this again will generate a swept volume that's going to capture all of the design space that the cable is passing through. And we can export it out in any of those formats mentioned previously, so that you can bring it back into your CAD or PLM system and really allocate that design space. So we can see our motion volume here. And I'm just going to change the color and transparency a bit so we can take a look at how our cable is moving through this space. So very easy to feed these changes back to any other systems you may be using. Another thing that's very interesting here is thus far we've been really taking a look at this cable with all of its nominal characteristics, right? So we're looking at it with the nominal length, nominal fixation points, nominal material properties, but we can also allow any of those things to vary in the tool and create tolerance envelopes that show how any of that variance would affect the design. So I'm going to pull up the tolerance envelope tool here. And you can see that we can allow any number of things to vary. So we could allow the fixation points to vary either in position or orientation, length, material properties, and we can do this with or without a motion. So just as a simple example, if I were to allow this cable here to vary in length, let's say plus or minus 10 millimeters, I can generate this volume and you can see all of that design space captured. And again, we can very easily export these things out to feed them back into any other systems that they may be needed in. And that concludes the cable simulation portion of the demonstration.
Great, thank you very much for that, John. That is impressive, especially being able, as you mentioned, to take the CAD data that you've used in IPS, bring it back into your CAD system as part of the product development workflow. A couple of questions have come up. How do you'd mentioned cable and hose properties? How are these determined? Is there a library of data that you may be able to reference?
Yeah, absolutely. Great question. So the tool does come with a library of predefined cables and hoses that you're more than welcome to use. And there are several other ways we can define material properties in IPS. So we can use basic parameters, right, which would just be density, Young's modulus, Poisson ratio. And this assumes basically a homogeneous material throughout your flexible. We also offer through our partners in Germany testing services. So they've developed a tool called the Mesomics test bench. And if you're doing a really critical application, in many cases, these basic parameters are plenty good for getting an idea of how your flexible is going to behave. But if you need a really in-depth look at internal forces, just a more robust study, we can send those flexibles out for testing to determine exactly what these effective material parameters are through our partners in Germany.
Great, thanks, John. Another question has come in as to, is there a force element as an output to understand how much force is acting on the cable? You've identified a number of measures. Yes, please go on.
Absolutely, yes. So any of these value measures that we've created, which keep in mind, there's a wide variety that we can track on the cable. We can absolutely output those and send that data into, some other system by creating one of those analysis plots, right? So if I create a plot, let's say for my bending radius, just as an example, I could send that information out either just as the graph in an image format, or we also have the ability to save this out in a CSV file that could then be used in any other engineering tools you may want to bring that data into.
That's great, John. And is when you say the force, that's forces on the cables as well as on the connectors or fittings or what have you, right?
Yes, absolutely.
Great. Well, with that, I think it looks like we're wrapped up with the cable simulation portion. I'll keep the mic on you, the spotlight on you to talk about path planning.
Awesome. Thanks, Carl. Yeah, so moving on to the Path Planner tool in the IPS toolkit. This is a solution that allows us to find collision-free installation paths for essentially anything. So those could be components in assembly. They could be pieces of tooling. So in this case, we're going to take a look at this damper, this hook style lift assist that's trying to pick this engine damper out of a dunnage tray. But if you have something and you want to find a collision-free path from position A to position B, the software can absolutely do that for you. It is extremely easy to use. Essentially, we just tell the software where to start, where to end, and what to avoid on its way from point A to point B, and the software will do the rest. So if I select my damper hook, and I'm just going to open up the rigid body path planning tool, I'll set this position as the start, and then I'm going to jump my hook into the final position. where it's actually hooked into this spoke on the damper, which is where we'll begin pulling it out of the tray. And I can set that position as my goal. Give the software an area to try to find a collision-free solution in. So you can see this box here that it's identified for me automatically. And then just click plan. And the calculation times can vary depending on the complexity of the installation path and how small the clearances are. But you can see that the software just found this installation path in about 7 seconds. So this is a very unique tool, very different from other simulation tools we see, where you have to manually manipulate each of the points along this installation path. So IPS is going to do all of this automatically for you. So now if I open up my motion here, and I'll slow it down a bit and click play, we can see our hook moving from that initial position into the final position. Now, one thing you may note here is that this path looks quite unrealistic to how an operator may perform this task. But keep in mind that this is just the initial solution. So within the Path Planner tool, I can smooth this motion. So let's say I'll smooth it 20 times to create a more realistic installation path that can then be used in conjunction with our IMA, our dynamic human modeling tool. So if I open my motion up again here and I'll slow it down, we'll see a much smoother, more realistic installation, similar to how an operator would probably actually perform this task. And again, this is all done automatically and very quickly. One other thing I'd like to mention here is that we also have the ability to create things like collision tests and distance measures. So I'll create a distance measure here, and we'll see our minimal distance tracked in real time, just as all of our other value measures were for the cable simulation. And we can see what that minimal clearance value is throughout the entire motion. Once I'm happy with the path that I've created, all I have to do is click Save to Scene. And now this installation path is available to use with any of the other simulation tools in the IPS suite. And that concludes the Path Planner portion of the demonstration. It's quite simple to use.
Thank you, John. Hey, we have a question from our participants, which is how can I exclude parts within the Path Planner that are barely touching? You mentioned collision detection.
Yeah. So if the so there's a few ways to do this. If you are actually in collision in your final position, right, your final installation position, there is a tool built right into the rigid body Path Planner that is called Auto Escape. So you can use this to try to find a position where it's just barely out of collision to get your final installation position. The other thing we'll often do is just kind of barely pull it out of collision, right? So we could look at something like this distance measure and use that to get an idea of how close we are to some other component. Or let me open this back up. We can very easily create a collision test. So you can see that also popped up in the bottom right-hand corner of the screen. And then this will identify when we are in collision with these components. And there are a couple of different settings for this. So let me just edit my collision test. So we can have it right now, it's just highlighting anything that's in collision. But what may be more interesting is we can take a look at intersecting lines or colliding triangles, which will give you a really good idea of where it's actually colliding. So let me change the transparency on this tray so we can get a better sense. And you can see where that collision is occurring exactly. So if we had two components that were barely in collision, we can use these tools to identify where that's actually occurring. and try to move it into a position where it's just barely not touching. I should mention here also, this is an interesting feature. You can also capture this geometry just by right-clicking on the collision test. And now I've captured these lines of where this collision is occurring, so we can export this out and feed it back into like a CAD system or somewhere else that this information may be useful.
Great, John. Then it looks like that provides a lot of information there that is actionable for solving a problem like this. The another question that's come in is we're working with tooling, but what if we wanted to install that the damper on a vehicle, or if we wanted to find a path that the trolley with the dunnages is going to take through a plant floor? Are those all things that can be analyzed with Path Planner?
Absolutely. Yeah, absolutely. So any two components or any two objects, items, if you want, just going from a point A to point B, the software will find a solution to get between those. And the other thing to mention here is that we have a very wide array of settings and options within the tool to really optimize whatever our path is. So we can tell the software to prioritize, avoiding obstacles or trying to find a very short path. We can have it prioritize rotation or translation. And we can even do things like constrain the path along certain axes, right? So in the example you provided with a trolley, we would constrain that to the floor plane, the XY plane, and not allow it to move in Z. And the software would absolutely find a path along the floor from point A to point B.
Excellent, very good. And I see another question, and you might have the right panel up there. What if it can't be done? How does Path Planner handle unsolvable paths?
Yes, so that is a great question. Typically, I'll allow the software to run for maybe a minute, and if it doesn't find a solution, I can increase the calculation time to allow it to run for as long as it is required to find the path. So very worst case, you could allow it to run for a few hours while you go and work on something else. But I will say that it will not necessarily tell you that you cannot go along some path or that no installation is possible whatsoever, just simply due to the fact that there are an infinite number of potential paths to try, right? But for instance, if we were to take a look at a plot of our clearances here between the hook and the damper, we're talking about sub-millimeter clearances on this installation path that it found in 7 seconds. So if the tool is really struggling for a long time to find a path, it's probably, if it were feasible, it's going to be such minimal clearances that it's probably not realistic, right? So if there is a way to get from point A to point B, the tool will find it. If there is not, it will not explicitly tell you that, but you can sort of infer based on the amount of calculation time.
Great, thanks a lot, John. With that, I'll turn the mic over to Kyle to talk about IMA, our intelligently moving mannequin, and how that fits into what we're doing with process virtualization and ergonomics. Hey there, Kyle.
Great, thanks, Carl. All right. Also, to John's point, in the sake of conserving bandwidth, I'm going to stop my video for a brief moment while I walk through the demo. So what we have here is a module that's called IMA, and really the purpose of IMA is to consider the human element during various installation paths. So in this case, what I've done is I've basically directly imported the motion that John was able to plot using the rigid body path planner for this hook. And now we want to evaluate the effectiveness of a human's ability to basically perform that installation. So creating a human in the IPS software just involves importing one from this mannequin family window. So you can import what's called a mannequin family, which is a series of mannequins. This can be, this is useful in sort of evaluating smaller mannequins all the way up to larger ones simultaneously. But in a lot of cases, you may just want to consider a single family mannequin, depending. So there's a data set that you would select from. So you can pick from answer or IFPS that are included in the software package. Define a sex for your mannequin, and then also define the body mass in kilograms or stature as either a value or percentile. So for the purposes of this demo, I've just quickly imported a male here of 50th percentile weight and height, just to give me a sort of general representation to start with. And so I think what's really interesting about IMA is that it may almost be considered an add-on module to the rest of the IPS suite. So this human is designed to interact really nicely with all of the other useful components, the analysis tools that John has already showcased. It's a very fast and efficient way of defining some essentially parameters that the mannequin has to operate within. And then you can evaluate whether or not there's going to be a likelihood of success with again, considering the human. So if we take a look at our mannequin and it's in the scene tree over here, we can see that the first constraint is that they're connected to a floor plane. And if we query the floor plane constraints, we'll see that the mannequin's allowed to translate infinitely along the X and Y axes, but is not allowed to translate up in Z. And that makes sense. In this scenario, they can walk sort of freely around the workspace, but obviously we don't want them to translate up in the Z plane. If we know and want to constrain a workstation pitch, we can define those characteristics. So for now, I've just gone ahead and defined a 500 millimeter by 500 millimeter workstation pitch. And you'll see that the mannequin already hopped to be located within those constraints. If I move the workstation pitch within my mannequin's base of support, they won't move because there's no need to. And then as soon as the mannequin observes that, hey, I'm outside that range that was defined for me, they're going to go ahead and adapt accordingly. So now the mannequin is located nicely in the workstation pitch right in front of where I'd like to see them operate. And so now I can begin to have them perform the task. A lot of typical, digital human modeling tools will require sort of manual manipulation of various joints or motions, things like that. In the way that IPS takes an approach to that is pretty unique, and I'll show that in just a minute. So as I was going to, get him to reach up here, we can see that, immediately the mannequin is able to pass through some geometry. And it's pretty easy for us to constrain that. What we do is we go into the mannequin menu and enable what's called collision avoidance. We can then define, much like the other modules in the path planner, we can define the geometry of concern. So I want to make sure that my mannequin is not going to pass through any of this highlighted geometry, and I can select OK and continue moving forward. So to essentially ask my mannequin to perform this task, it's pretty straightforward. I'm going to select the item in the window here, and then I'm going to add what's called a grip point to that object. As soon as I query this grip point menu, I'll see a representation of the target location for my mannequin's hand, in the hand style that you select. So whether that's a right hand or a left-handed grip. In this case, I think a right-handed grip is most appropriate. And then I can then begin, manipulating my hand until I find that, it's a pretty reasonable position for them to be grasping. And that looks quite good there. Now I get the opportunity to define a specific type of grip. And so much like the cable sim, there is a library that you can pick from of sort of predefined hand postures that could be useful for different tasks. So if it's a wiring connector, you may want to look at the tip pinch. So if I select that, you can see how the posture of that target hand changes. But for this task, I think a cylindrical power grip seems most appropriate. And you can see that actually looks quite good. And now I have the ability to either expand or close my grip, again, just for sort of the sake of clearance and realism. And I think that positioning there looks quite good. In the sake of, again, defining parameters that the mannequin needs to operate within, there are grip settings that also allow for tolerancing. So in this case, I think the mannequin can comfortably tolerate about 20 millimeters up and down the sort of the vertical length of this tool. They can sort of position their hand anywhere they'd select along this length here. So I'll give them some translational tolerance in this direction, and then I'll give them a little bit of rotational tolerance again as well, just to ease the calculation. And I think it's reasonable that a mannequin can flex or extend or deviate in some capacity from this exact target. But if the intent is that this is the exact target, you can set all these values to 0, and then the mannequin will have to achieve this very specific orientation on the task. So once I'm comfortable with the positioning of my grip point, I'm just going to select done, and then I'm going to drag and drop that onto my mannequin. They will then reach up and grasp that target location, and it's confirmed that they can reach it by this small little green dot here on the grip point itself. And since my grip point is actually nested, in the tree structure here, my grip point exists underneath this object here. Since John's gone ahead and plotted a path for that object, it's pretty easy. The grip point is going to sort of follow the length of that route that's already been plotted. So if I go ahead and select play here, you'll see that my mannequin's trying to follow that path. You can actually see if I pause it right about here, you'll see that the icon for my grip point's actually changed. It's no longer green. It's now displaying as sort of this red with a cross-hatched line through it. And basically what that's telling me is that, based on the constraints that I've set, constraint to the floor plane, collision avoidance with this CAD geometry, and the tolerancing that he's been allowed to deviate from this grip point, all of that considered, he's been unable to find a successful path to again maintain that grip. And you can pretty clearly see why, right? If I render this, you can see that there's essentially no tolerance for a human hand to be able to achieve this task while still maintaining a cylindrical power grip on this tool. And so one of the ways that we can quickly validate design changes is by simply swapping this tool and swapping the grip point. And so we'll do that right now. I'm going to go ahead and release my grip from this tool. I'm going to go ahead and hide this tool. And I'm going to bring up the proposed design change. And what that looks like here is a tool that's got a 30-degree bend in the actual sort of hook mechanism. And what that should allow us to do is to grant a little bit of a better clearance to the actual geometry around it. You can see that as I play through that same motion that would have also been created using a path planner, you can see there's much greater clearance between this part and the surrounding geometry. So if I bring that back to its initial position, I go ahead and I grab my grip point and I attach my mannequin to my new grip point. You'll see that it's confirmed they can reach the target location in its base state. And now I'll simply play through this motion and observe to confirm that this is a successful path throughout the motion. And you can see that pretty clearly. The motion's unchanged. He's demonstrating pretty clear clearance to all of these CAD geometries. And so this is a successful redesign, in my opinion. Another thing that we can do is using IMA, we can get a good understanding of what the mannequin is able to observe through the course of their task assignments. And so we can do that through the use of what are called viewpoints. So again, I'm going to select my tool. I'm going to select this icon up here, this eyeball. And what that's going to do is it's going to release a grip point in the location of my tool. I can then, what I'll do beforehand, I will bring up what's called the vision analyzer and bring up a window so that you can essentially see exactly what the mannequin sees. So you see that there is this view window. They're sort of looking off in space. And again, playing through that motion, we want them to actually target this location on the tool. So it's as simple as dragging and dropping that viewpoint onto my mannequin. And you can see that my vision camera has updated. I may just quickly hide my grip so you can see the mannequin's hand a little bit more clearly. And again, as you drag through this motion, you can see exactly what they see. So you may want to consider, adjusting the grip point and, producing just recommendations based on, hey, it seems that they may have difficulty spotting this based on how they've, initially selected the grip. And this can also release, new ideas for product or design changes. Another really neat feature about IMA is the ability to assess from an ergonomics perspective how difficult some task or assembly may be. And that can be done by opening what's called the static evaluation. So we can see here that based on the current posture that he's in, it gives me an output for essentially the estimated level of risk given the postures that he's assuming. So there is a biomechanical model behind IMA, consisting of a series of joints and segments. I believe it's 84, but I can confirm that. And each one of the joints and segments is being monitored in real time, much like the other components of IPS. And you can query this and quickly identify that the arm and wrist are at the greatest risk, and the overall score for the task is a level 4. So if it's a level 4 for say a 50th percentile male, we may want to do some further investigation and confirm that this task would be viable for, say, a smaller, shorter female. And so we can do that by hiding my male mannequin and releasing the grips and resetting my simulation. There we go. And what I'd like to do now is quickly bring up a mannequin family. So a mannequin family can consist of any number of mannequins. In this case, I've selected 2. I've got a smaller female and a taller male. So this should give me sort of a good indication of basically the level of risk associated for a population ranging from small to large. So what I can do here is I can, similarly as I did with the individual mannequin, I can look at my lift assist, look at the grip point that's embedded behind it, and just drag and drop that onto my family. We can see that in the start position, it is green, so it looks good. So that means the start position, there's no issue with the mannequins reaching that point. And we can then go ahead and play through this motion. It actually stayed green through the whole time, so that looks good. That means the outer sort of perimeter of this task looks quite good. One other thing that we might want to consider is that at certain points in time, they will need to reach to parts on the inside of the bin. And so we can look at that as well. So if I move my mannequins back a little bit and go ahead and change the position of my trays, and then basically reattach my mannequins to that grip point, I'll be able to play through this motion and see, using the collision avoidance, are my mannequins able to successfully reach that? Go through and play. We do observe that at a certain point in time that this is going red. So it's brief there, but you can see that the mannequins will have a difficult time reaching this if they are smaller. You can see that their posture is a little bit compromised. And we can again open that evaluation and see, based on the range of mannequins that are located in our sim, we can see that the grand score is actually significantly more red for the smaller female than it is for the taller male. So one thing that we might want to consider doing is either reducing the complexity, the number of trays that would be included in this so that the mannequin doesn't have to reach as high. Alternatively, we could look at, doing something like raising the floor plane up. So if in real time I bring this floor plane up, what we can do is then again, query that family, open the static evaluator, and confirm that this has significantly reduced the risk. And it's gone from that sort of dark red maroon high risk state up to this sort of, from a posture standpoint, this much improved sort of yellow to green state. The last thing that I'll say about IMA is that it doesn't simply need to evaluate these sort of static one-off single tasks. You are able to open what's called the operation sequence editor. And this is a really powerful tool that allows you to basically stack different tasks together. So you can start with, a single mannequin, import some parts that have basically these motions applied to them, and then have your mannequins performing various tasks. So if I want, say, a mannequin family, I'm just going to delete the individual mannequin. I'll bring my mannequin family in here. It applies a start state to them. I'm going to go ask them to, if they're grasping any grip points, they should begin by releasing that grip point, and then grasp and follow the motion of that. You can then continue to add different objects and actors in the scene that, again, will continue to follow additional motion paths, and start stacking those together in a very sort of like linear timeline that allows you to, in a single click, press play, and it'll generate these series of complex motions where mannequins can be walking through the scene, grasp a part, follow a motion, release the part, assume a posture, grasp another part, and you can stack these very complex series of motions together and end up with an ergonomic output that's representative of a much, much larger series of tasks. So it's useful for point in time assessments like this, where you can identify sort of the worst case scenario, but also basically stacking together certain elements of a process. And so with that, that concludes the IMA portion of this demo.
Thank you, Kyle. You've provided a lot of great information here, and we do have a couple of questions that have come in. On that, you had shown an investigation of or an evaluation of the posture. The question is, are there other kinds of biomechanical analyses available within IMA?
Yeah. So at this point in time, the mannequin is primarily either assessing the viewpoint, again, either for reach, for clearance. So again, much like the other tools, the distance measurements that John has shown, you can query distance measurements for hand clearance between, mannequin geometry and surrounding parts. So reach, hand clearance, visibility, and posture, those are the primary ones. We are working to implement in the future a biomechanical strength model. This is something that we expect to have in beta sometime in early 2023. But at this point in time, there is no, say lumbar compression analysis or, shoulder analysis, but we are working to implement, one of the more recently published, shoulder strength models into this tool in 2023.
Excellent. Does that, in the case of the tool example you're showing, does IMA take into account the weight of objects in this assessment if they were using a heavier tool?
It's a really good question. Thanks for asking that. Yeah, so the tool itself doesn't necessarily carry any weight, but the grip points do. So whenever you have a grip point in your scene, you have the ability to edit that grip point, edit the grip point and add a mass to that object. So let's say we make this 10 kilograms. If you watch the mannequins carefully, they will adjust from a postural standpoint how they are approaching that task. Again, because there is no, I'll say, strength model, there's no ability to, extract whether or not they could successfully, from a strength perspective, complete the task. But again, applying a force or a weight to the grip point itself will allow them to change their posture, and that will also affect your, your basic RULA, your rapid upper limb ergonomic assessments from the posture standpoint. So as they are adaptively changing to the new added weight, that may have an impact on your ergonomic outputs.
Thanks, Kyle. What if you wanted to develop a situation where two of the mannequins needed to work together? Let's say to lift one of the dunnages. Is that possible?
Yeah, absolutely. So, so the purpose of that would be, I guess, twofold. One, to evaluate, again, from a posture standpoint, how a mannequin might approach a task, and so say like something like this piece of dunnage was the task. One person could potentially lift it from the side here, but that might be a little bit awkward. So you could look at a two-person lift and put a mannequin on each side of this, each with a left hand and a right hand grip point. And what that would allow you to do would be, taking if you have the known weight of your, your object, you'd be able to obviously edit the mass and reduce that significantly, assuming like a homogeneous object and thing, and the weight's not shifting. But what it would allow you to do is just basically change the weight so that each mannequin is sharing the load with the other. So that's really, but again, those grip points would act in unison. So as the mannequin performs the motion, say this object is moving from point A to point B, those mannequins would lift that together. So you can have, 2, 3, 4 multiple mannequins all following the same motion and task.
And it's great that it really leads to being able to do a complete analysis of how of workstation operations and how an operation like this could work in concert.
Right.
Oh, great. I'm not seeing any more. Oh, wait. Questions on the IMA side, so I'll let you continue and move over into virtual reality.
Great, thank you. Okay, so I'm going to go ahead and open up our scene that we have prepped for VR. And I might just take a brief pause here and tell you a little bit about how this is set up, just so that it's pretty clear. So you'll actually see my mouse. If I won't touch my mouse for a brief second, and if you see it move on the screen, that's actually John controlling my mouse remotely. And so what we have here, and I think what makes part of the approach that IPS has taken towards VR, what makes it unique, is that it allows somebody to operate using a VR headset in unison with somebody directly, in real time controlling the full desktop suite of IPS. So this would probably be more likely done with 2 people interacting in the same room, say within a lab. Ultimately, I'm in Canada and John's in Colorado. So we've done this remotely. But what you'll see here is I'll be in my VR headset. And John will be operating the desktop controls while I'm sort of interacting in using the virtual reality controls. So hopefully we'll try our best to make this as clear as possible. But yeah, that's the situation that we have set up right now. And so one thing that's worth noting is that IPS's VR approach leverages Steam VR for connecting the hardware to the software. And really what that means is that the ability, the variety of devices that you can connect to IPS is pretty diverse. This will operate with all of the HTC products, all of the Meta or Oculus line of products, Vario products, HP products. So it doesn't really matter what headset choice you choose to pursue. Know that there's a strong compatibility likelihood with IPS just because it uses the Steam VR. So let's get this started. I'm going to put on my VR headset. And John, if you wouldn't mind putting me into the VR mode. Perfect. All right, that's great. So I'm just going to stand up for a minute. I will adjust my camera so that you guys can hopefully see everything that I'm going to be reaching to in the scene. Okay, so thanks, John. So what you can see, John, if you don't mind pulling up my VR view, let me know when you've done that so I can, show everybody what I see.
I've got it.
Awesome. So you'll see in real time, I'm actually fully wireless, so nothing that's connecting me. I don't have any base stations or anything. It's all done through this headset, which is pretty unique. And what you can see is, I have some actions that I can do in here. I've got a pretty small subset of menu items that I can open and control what's going on in the scene. But really the use of this is that John has access to the complete desktop suite, and he can really help me along my VR journey while I'm in here. So John, why don't you actually go ahead and take that mannequin? Let's strap that to me so I can get a feel for what it looks like to be a little bit smaller.
Sure. Just a moment. Just drag and drop the mannequin onto you.
All right. That's awesome. Thanks, John. So you'll see that I actually have full control over the mannequin. As I move, they are going to respond in real time. It's very fast. It's very accurate. So I'm going to actually go over to this seat here, and the mannequin's going to come catch up to me. So what I can do, I can actually go ahead and I can put my hands out. I can reach over to this chair here, and people, I'll be able to get a good flavor for how far a mannequin can reach, while also, ensuring that I'm not, contacting this conveyor or anything like that. And this will also work with all of the collision avoidance. So I can enable that as well. But for the purposes of this demo, I think it's pretty easy to get a flavor for what it feels like to be somebody who is a little bit smaller in stature than what I would be. So I'm actually going to go over here, and I'm going to actually attempt to pull that piece out of the rack there. It's pretty high, so you'll see that I actually have to reach quite far overhead and go ahead and grasp that part. So let's say, John, number one, can you take the mannequin off me? It's a little bit distracting for a quick moment here.
Sure.
If you don't mind.
Sure. Just de-render her.
Perfect. Thank you.
And let me.
Yeah. So John, this was really quite high. Do you think you could lower that? I'm going to grab this, and I think this height would be a much more appropriate height. Do you mind lowering the stock bin to that height for me?
Yeah, absolutely. One moment. How's that?
That looks good there. All right, I'm going to go give that a try. I'm going to go put this and to see if I can put this piece back into the bin. 1 second. There we go. And you'll actually notice that we have collision avoidance basically with the VR as well. So as I sort of grasp this part, and if I try to slide it into that bin, it's going to collide and respond. So you can imagine there can be these scenarios where you might have a part that needs to be installed very, in some tight quarters. It's going to, you're going to get a good flavor for that because it's going to bounce off any geometry that it really shouldn't pass through. So John, what I'm going to do here is I'm going to actually try to perform that task install. I know it's got to be installed to the seat there. So I'm going to go ahead and select record my motion. And I'm going to go ahead and grasp it. And I'm going to pull it out. This looks like a two-handed install for me. So I'm going to go ahead and turn around and place that into the seat there. That install looks good to me. So I'm going to go ahead and turn off that motion. And if I step back for a second, John, can you actually replay what I just did for me?
Yeah, absolutely.
See how that looks.
Let me just get to a little better view here. And I'll set it to repeat.
That's awesome. Okay, and I can actually see my hand on there. And so what's interesting about that is that grip point is exactly where I left my hand when I grabbed that part. And we can then use that grip point in the IMA function and apply another virtual human to that. So we get the digital human grasping the part as naturally as I did, the way that it felt comfortable to me while I was in VR. And they would then be able to follow this exact motion path. The other thing that's really interesting about this is that the actual timing that it took me to perform this task is accurate in this motion. And so this could be something that's really interesting to, say, industrial engineers, to really make sure that people are able to perform the task at a specific or a given, rate, so that they can keep up. So that's good, John. Do you want to stop that motion for a second? I'm going to go hop over and showcase the cable. All right.
Yeah, absolutely.
I'm going to hop around the scene here. And then, John, let me know when you've come and found me.
Sure. Yeah, just 1 second. Let me make sure we've got a good view. And then I'll actually try to 1 second, Kyle. I'm just trying to get the VR view and the
Great.
IPS view.
Yeah, this would be a good one to see through my eyes.
Together. And then let me just make this a little smaller. Okay. So now we can see IPS as well as the desktop client, as well as Kyle's view at the same time.
Awesome. Yeah, so I know that this will be my task that I need to complete. So I'm going to go ahead and actually grasp that part, pull it out a little bit. you can see that as I pick up this part, the cable is actually going to respond dynamically. We've actually got collision avoidance turned on. So, basically this cable is going to crash into the seat and it's not going to translate through it. Also, what's really interesting is that if I apply any tension on this cable, it'll apply the same visualizers that John's got on earlier. So I'll be able to see whether that's torsion, if it's stripes, if it's violating minimum bending radius, if it's violating some total force or tension in the cable. I'll be able to see that happen in real time as I apply any tension. So John, maybe jump over to the desktop so they can see what it looks like if I accidentally perform this assembly incorrectly.
Sure.
So see, if I grab this part and I accidentally try to wrap this around the wrong way, you'll actually see that it starts to collide. It starts to maybe, display those red colors, giving me a pretty clear indication that's not the right assembly path. So what I'm going to do is I'm going to grasp it and I'm going to apply it the correct assembly path. But to me, like this might be a concern. This is a pretty tight area for me to get my hand in. So what I'm going to do is I'm just going to put my hand in. Oh, sure.
Sorry, there we go. Back to a better view.
No problem. You can just see that my left hand here, if I go to grasp that part, it's pretty tight for hand clearance. So what I'm going to do is I'm going to leave a grip point for myself. And I'm going to go ahead and take that back into my IMA module in a little bit. And I'm just going to take a look at how much clearance I've got between this seat and that part there. But yeah, that looks great. And that concludes the VR portion of the demo.
Great, thank you, Kyle. You just touched on a couple of questions that we had, which was whether you can record the VR session and then use it back in IMA to do the ergonomic analysis.
Exactly. Yeah. So I'll just reiterate. So when you're in the VR, you have the ability to select record motion. And when you do that, any parts that you pick up and move through the scene are tracked in real time. And again, you can see that just, due to the nature of artifacting, you can see that there is some choppiness to this, but we would be able to smooth that just like every other motion that comes from the path planner and things like that. So the raw motion data might be a little bit choppy. After John puts it through 10 or 20 cycles of a quick smoothing, you'll see that data be nice and filtered. And then you can then use that for training elements or whatever it may be. But it is really useful to be able to play back in real time exactly what you performed while you were in the VR setup.
Excellent. And then likewise, so that's the IMA to VR connection. In the case of the cable, if you found that perhaps extending the length of the cable would be of use, do you have access to the cable simulation functions from VR?
I do, yeah. So in those menus that I was able to show, there's some, we'll say, limited functionality that's available to the VR user. But I almost see that as a strength because I've seen other VR tools with far too many capabilities that they try to allow you to access in VR. So you're sort of menu diving, right? It's very difficult to create a nice user interface for VR use. So I think what's really nice and unique about this implementation is that somebody could be on the back end, again, using the full powerhouse suite of the desktop version of IPS, and they have a lot more access and control over features. But basic things like segment length changing, I can do that while I'm in the VR headset. Yeah.
Excellent. And to the question of the equipment, could you talk about the equipment that you were using for the demo and what types of
Sure.
equipment types are supported?
Yeah. So for my demo, I'm using this is called the Oculus or Meta Quest 2. Some other I guess VR hardwares might have like little base stations that need to be hung or mounted. This headset is nice because it operates fully wirelessly. It doesn't need anything mounted. So it's a pretty freeing experience. You can imagine if I was in a gymnasium or some open concept space, I can freely actually walk and move. You'll have seen that I was sort of jumping in VR here, but if you're using an untethered wireless VR device, you can actually just physically walk around the room and it feels very natural. And again, to the point of time studies and things like that, that can be really useful. So the hardware choices are sort of endless. Really, all of the major VR devices that are on market today would be supported by this tool. So yeah, there's a lot of flexibility here.
Great, great. Thanks for that. And yeah, with that, I think I was going to go to a closing slide on my side, just kind of showing the world of possibilities that we have in our IPS industrial path solution simulation environment. A question also that came over, and I'll pose this to John, is the types of interfaces to CAD PLM systems that are supported, since the working together in a process workflow is quite important.
Yeah, absolutely. Great question. So there is an out-of-the-box direct connection between PTC Creo View and IPS. And we've actually seen some clients use this very successfully, right? So it's a one-click integration. Essentially, if you can open up a piece of product or tooling in Creo View, you click one button and it sends it directly into the IPS tool. We have also seen some direct connections between Siemens Teamcenter and IPS, so we know that those connections can be established as well.
Excellent, excellent. Well, I appreciate you guys demonstrating what the power of the IPS tools going through. I think we completed the workflow that we'd set out to, looking at cable simulation to path planning to ergonomics with IMA, and making the entire thing accessible in virtual reality. So with that, I know there are a number of folks that, or a couple of folks that had to drop a little bit earlier today. So to all the participants, attendees today, we will make a video of this webinar available to you once we do some minor edits on it. And of course, you've been in contact with us through the invitation you received either from Sandalwood Engineering or Flex Structures. If any of the various applications that we showed you are of interest, or if you've got a question or challenge of your own that you'd like us to look at, we'd be happy to partner with you to be your solution provider in an exciting and emerging space here. There's a strong movement afoot to go to 100% virtual validation for product development and assembly manufacture that we're seeing throughout the transportation sector, and it's only made more challenging by the increased complexity of vehicles and the systems building them. So we'd be excited and honored to work together with you. Again, I'm Carl Bangert on behalf of Flex Structures, and John and Kyle over at Sandalwood Engineering and Ergonomics. Thank you all for your time and